Okay, so here the philosophy is okay. So this is called a relational. Dirac observable is constructed relationally. Constructed relationally. So what we mean by relationally, it is like what I emphasized earlier, is that you are parameterizing your time by using the arm of the clock, but you parameterizing the motion of any object by using time, right? But time is parameterized by the arm of the clock. So which means that you are actually parameterizing the motion of any object by using the arm of the clock. So you are parameterizing the motion of object by using the motion of another object, right? So this is the philosophy behind this construction of Dirac observable. So here you are parameterizing the motion of the gravitational field by using the motion of matter field, by using the motion of dust field. And the dust field behaves like a time parameter, behaves like a reference frame. Okay, so this is what we call relationally construct Dirac observable. Okay, taking as reference. Okay, and second advantage of this construction is that the result Dirac observables satisfy nice Poisson bracket. So here you can see you use four you use four dust fields to parameterize gravitational field, and the gravitational fields, the gravity canonical pair, they are metric and extrinsic curvature in ADM formulation. So you can compute corresponding Dirac observables. Okay, so Q, like we construct above, but similarly you can construct the P, the extrinsic curvature in ADM formulation. Then you can compute the Poisson bracket. Okay, and you find the Poisson bracket is more or less the same as the standard Poisson bracket. So by some computation, you can show this. It is also easy to understand because what you do is actually just you consider a specific coordinate, which is given by the matter field. And then, of course, the Poisson bracket will be the same as before, depending on, and here you just get delta function of the new coordinate. Or if you want to use Ashitaka variable, it's the same before. But here, well, we have to change our notation a little bit because now we use ij to be the coordinate indices in the dust frame. Before we use ij to be Lie algebra indices. Okay, so we have to interchange the role between ij and ab. So here now we use a and b in this formula. So in this, when we do reduced space-based quantization, because I and j is indices for the dust coordinate, So we have to use j and k to be the space-time indices, but a and b to be the Lie algebra indices. Here, a, b are SU2 indices. Okay, before we use AB to be space-time indices and IJ to be the SU2 indices, but now we interchange this convention in the reduced space-based quantization. So it makes the formula. You have to be careful about formulas. All right. Now you see we have, again, canonical conjugate pairs, and they are the canonical conjugate pairs in the reduced phase space. Pairs in the reduced phase space. Okay. You can also count in the degree of freedom. So before, you see, let me see. So because you are using this dust field to be your time parameter. Okay. So let me just do counting degree of freedom. So so in the unconstrained phase space, you have A, E, T, P, and TJ, SJ, TJ, right? This is your conjugate pair. So A, E, they are, so I ignore indices for A and E. So A and E are for gravitational field, and TP and SJ, TJ, they are for dust field. So this is the degree of freedoms on the unconstrained phase space. Okay, and now on the constrained surface, so again, you have A and E. So when you solve the constraint, you solve P and PJ, right? So on the constrained surface, you get rid of P and PJ because you solve them. You solve those constraints. So you only have T and SJ. Okay, so these are the degree of freedom on the constrained surface. But now you model out gauge freedom. Yeah. So because by using fixing the value of tau and sigma, so you get rid of four degree of freedom. They are gauge freedom, right? And so you fix the value of tau and SJ by T and SJ. Okay, so or you model out gauge freedom because gauge transformation transform T and SJ. Okay, and so now when you come to reduced phase space, so now you only get A and E. So now but A is parameterized by tau and sigma. E is parameterized by tau and sigma. Okay, and you get rid of T and S. So in the end, the parameterization or the coordinate on the reduced phase space is just parameterized by, it's just a gravitational field, but the gravitational field parameterized by the dust field, tau and sigma. Okay, so here A and E, they are canonical coordinate, canonical conjugate pair for the reduced phase space, and you don't have other degree of freedom anymore. Okay, so this is just a counting of degree of freedom. So here, so you see it is important to couple four scalar fields. And one scalar field corresponds to time, and the other three scalar fields correspond to space. And then here, by counting of degree of freedom, and in the end, on the reduced phase space, you only left with gravitational field, and all the dust field become parameters to parameterize gravitational. Okay, so that's why. So if you have, that's why you have you use four degree of freedoms for the matter field, for dust field. Okay, so now you have a reduced phase space. You are clarified, you clear about reduced phase space, and the reduced phase space is just a manifold which is parameterized by A and E, satisfy the same Poisson bracket as before. So you just view, okay, so now you have a coordinate that satisfy this Poisson bracket, okay? And it is now unconstrained. You have no constraint anymore because you have reduced phase space. But the structure of the phase space is the same as the pure gravity phase space. Okay, but now it is a reduced phase space because it is you start with a gravity coupled to dust. And on this reduced phase space, you have a physical Hamiltonian. The reason is that you have physical time tau. You can understand, you can study the time evolution corresponding to this physical time. Yeah. So you have a time already. You don't have problem of time because you have a time tau. You can talk about time evolution. Physical time Hamiltonian for the dust field, and this for the dust time or physical time. And this physical Hamiltonian, as a result, I'm not going to give you the derivation for that, but the result is that, remember, when we solve the constraint, when we solve the Hamiltonian constraint, you get h p equals to h. This h is square root of c squared minus 2ab, HCACB, and this h, if you integrate over the sigma, the dust value, the dust field value sigma, if you integrate h over that, you actually define the physical Hamiltonian. Okay, so this is the physical Hamiltonian. This equals to, well, h sigma. Well, h in principle depends on tau and sigma, just like Hamiltonian density, but it turns out that you have a conserved quantity. It's the result doesn't really depend on tau. C sigma square minus Cij. Sigma. So here I write Ci sigma and Cj sigma. It doesn't depend on tau. The reason is that the Ci, Cj, they are actually conserved quantity as well. Okay. So maybe so what is this C and Ci? The C and Ci, they are just the gravity part of the Hamiltonian constraint and diffeomorphism constraint. Okay. But now replacing all the variables by Dirac observables. So this, for example, this C, tau, and sigma equals minus 2 kappa trace of ij. So you just replace everything by using corresponding Dirac observables. And here you get commutator, the algebra commutator. Well, this is the Euclidean part of the Hamiltonian, and the Lorentzian part of Hamiltonian you can write it down analogously. Okay, similarly, Cj tau sigma is 2 divided by beta kappa A sigma. Okay, so here, I emphasize it again that here A, they are Lie algebra indexes, Lie algebra index, and Jk, they are dust index. They are the spatial index in the coordinate, in the dust coordinate. Okay, so here I switch role in the reduced phase quantization. I switch role between Rome alphabet and Latin alphabet. Well, sorry, the A and JK. All right. So this is the physical Hamiltonian, and it generates the time evolution of Dirac observable. So if you consider time derivative, partial tau, any Dirac observable parameterized by tau and sigma, it equals to the Poisson bracket. This is something you can prove, and this is proven in the reference I give you at the very beginning. Okay, so the time derivative of the Dirac observable with respect to tau equals to the Poisson bracket between that Dirac observable and the physical Hamiltonian. So it means that the physical Hamiltonian H generate physical time evolution. Physical time evolution. And now here you have no Hamiltonian constraint and different movement constraint anymore. The dynamics is free of constraints, free of Hamiltonian and different movement. Okay, so now it is really nice because you get rid of all the constraint and you have a dynamics which is generated by Hamiltonian, and you don't have problem time because the dust field naturally give you a time. Okay, and now you can straightforwardly carry out quantization because in this model, the reduced phase space is the same as the pure gravity phase space. Yeah, now the reduced phase space is parameterized by A and E, and it is exactly the same as the unconstrained phase space for pure gravity. Yeah, but now it is reduced phase space. So now when we quantize, we can just quantize this reduced phase space just like before. So again, we introduce the lattice gamma. It is the cubic lattice in the space of sigma in our spatial slice, which is parameterized by the sigma space of sigma. So this is usually what we call a dust space. Dust space, and sometimes people use script S for this. Dust space. Dust space is just a constant tau spatial slice or the space of sigma. Now, the connection field, a Dirac observable connection field, regularized on the and discretized on the lattice, they give you a holonomy like before, and then when we quantize, you get holonomy operator. And the E field sensitized triad, again Dirac observable, parameterized by tau and sigma, and give you flux field, give you flux on the lattice. Here again, I use A to be the SU2 index instead of baseline index, and to quantize, you get flux operator on lattice. It's LP squared divided by 2 and right invariant vector field. Okay, like we discussed before. The quantization is exactly the same before, but now we are, so these are quantizing Dirac observables. Quantization of Dirac observables. Okay, so they are unconstrained observables. Well, I mean, they are. You still need Gauss constraint, so they are unconstrained because so they are not constrained by Hamiltonian constraint and different movement constraint because they are solved classically already. But we still have Gauss constraint, so we don't solve Gauss constraint at classical level. Well, it's easy to understand because you see for the Hamiltonian constraint and diffeomorphism constraint, when we consider coupled to dust, the matter part is very simple, so we can just solve P and Pj. But the Gauss constraint is still the same as before. The Gauss constraint is partial A, E, A plus commutator A and E. Okay, so this is the Gauss constraint equals to 0. But, well, it doesn't involve, firstly, Gauss constraint contains no matter part. And secondly, well, it's not going to work. It seems not easy to solve them classically because we still want to have A and E to quantize. So the Gauss constraint is still preserved at the classical level, but we know how to quantize Gauss constraint and solve Gauss constraint quantum level. Okay? So it's fine to just keep Gauss constraint and solve quantum mechanically. Solve Gauss constraint quantum mechanically, and then the result is just the Hilbert space of gauge invariant wave function. Hilbert space of gauge invariant function. Okay, and the basis is just the spin network functions. As before. Networks. Okay, and now this H gamma is already the physical Hilbert space. Because it has no constraint. We don't need to impose any constraint on it anymore because constraints are solved classically, and H gamma is a quantization of the reduced phase space. Okay, and we solved Gauss constraint already, so we don't have any constraint imposed on H gamma. So this is already the physical Hilbert space. But you can see that this framework is really powerful because we get easily the physical Hilbert space. Yeah, we easily solve the constraint, and we solve Gauss constraint quantum mechanically, and the reduced phase space, we understand the reduced phase space in this model, and we can just quantize reduced phase space and get a Hilbert space. And this Hilbert space is already the physical Hilbert space. We get it easily. But compared to the earlier approach, we have to impose a constraint quantum mechanically, but this constraint was so complicated that we are not able to solve those constraints quantum mechanically, and so it wasn't clear about what is the physical Hilbert space. But now in this approach, it is so powerful that in the end we just get physical Hilbert space very easy. So that's why this approach is nice and powerful, and this is very useful in recent study of loop quantum gravity. Okay, and so we got Hilbert space, and we are also able to quantize the physical Hamiltonian. Okay, and we can quantize the physical Hamiltonian to get the physical Hamiltonian operator. Physical Hamiltonian H, it becomes, we promote to be an operator, and this operator act on the physical Hilbert space. Okay, so this is the operator act on the physical Hilbert space. Okay, and we can explicitly write down this operator. So the quantization, so you see this physical Hamiltonian, it is just, it relates to the Hamiltonian constraint for gravity and diffeomorphism constraint for gravity. And we know how to quantize them in earlier lectures. We have done the quantization of the C and Ci. Okay, so we just plug in our earlier quantization. So we got this physical Hamiltonian is the sum over all the vertices to replace integrating over the dust space. Okay, and since we discretize the dust space by using a cubic lattice, so we only sum over all the vertices, and then again there's a square root and absolute value. Okay, and CV hat square and 1 over 4 1 over J 1 2 3 Cj according to our previous notation. Okay, so remember we have defined the operator CV and CJV. Okay, and it was the Hamiltonian constraint operator, and it was diffeomorphism constraint operator. we have to put a absolute value because those operators, those c square minus 1/4 cj square is not necessarily a positive definite operator. So we have to, at quantum level, we have to put a square root. So we have to put a absolute value and then take the square root. So these are the Hamiltonian and diffeomorphism constraint operators. But it was a constraint operators, but now they are just some building blocks for the beta Hamiltonian. There's no constraint anymore. Okay. To explain why there's 1/4, so you see, so here the classical expression is the Qij, Ci, Cj. So what we do here is that we write Qij to be E I A E J A. So here A, it is the Lie algebra index. It's the internal index, Lie algebra index, and Ij is the space-time index. And now we define Ca, okay, Ca to be Eia 2 times Eia Ci. Okay, and so we put a 2 here conventionally, so it was a convention, yeah, and that's why we have 1/4 to cancel 2 square, because you have 2 c's, so you have 2 square here, and so here I call the Ca, right? But in earlier convention I called Cj, because at that time we used J to be the Lie algebra index. Before we call it Cj. Okay. Before this is exactly how we construct the diffeomorphism constraint. So this Ci, before we called Ca, it was the diffeomorphism constraint with the space-time index. And now we contract with the tetrad and to get a modified diffeomorphism constraint, and we actually quantize the modified diffeomorphism constraint, and that one we call Cj, and J is the Lie algebra index. But now in this reduced phase space, I will call it Ca, because A in the reduced phase space quantization is the Lie algebra index. Okay, and when that time we quantize Cj as an operator. Yeah. So still I use the same notation as before. So that is Cjv, but now this J here is the Lie algebra index, and J equals 1 to 3. Or you can also, yeah, if you like, you can just call it Ca, K from 1 to 3. Well, anyway, but to use this in terms of operator, to use the same convention as before, to use the same notation as before. Before I called operator Cjv. So now I still call it Cjv. So hopefully you can understand what I mean. Okay, so now this operator, this is the definition of operator, Hamiltonian operator. Well, there's the absolute value. Well, this absolute value is the same understanding as the volume of, for example, volume operator. Volume operator, there was absolute value and square root, right? So let's say, and well, square root and absolute value of certain operator O is actually O square, or so O in principle O dagger O, and then take the 1/4. So it depends on O is self-joined or not. So in this case, this quantity inside the square root is not necessarily self-joined, because this is not, it is Hermitian, but not necessarily positive, because in the middle there is a minus sign. So this quantity inside this absolute value is not necessarily self-adjoint. So the absolute value, and then take the square root, is O dagger O, and O dagger O, it is positive. So you had experience on master constraint. If you understand master constraint, and you know O dagger O, it is permission and positive, so it has self-joint extension. Okay, and then once this guy is self-joint, you can find the spectrum and take the spectrum to the power 1/4. It defines the operator to the power 1/4. Okay, and again, the result operator, square root operator, is still self-joint operator. So this H is a self-joint operator. If you had experience of Hamiltonian, if you had experience on master constraint, you understand master constraint is self-joint, so it's easy to understand. This H is also self-joint. Okay. Okay, so now the reduced phase-space quantization. So that's all the procedure of the reduced phase-space quantization. You have the unconstrained physical Hilbert space, and you have a Hamiltonian operator on this Hilbert space. And now the situation of reduced phase-space for loop quantum gravity is similar to lattice gauge theory. Phase-space. Makes loop quantum gravity similar to lattice gauge theory. Lattice gauge theory, although you have a little bit more complicated, you have a more complicated Hamiltonian. Okay, because we are doing quantum gravity, it's not just the gauge theory. Well, now this it is lattice gauge theory because you get rid of all the constraints. You have no constraint. You have a Hilbert space, and you have your variables are holonomy and flux, and you have a Hamiltonian generating time evolution. And this Hamiltonian is self-adjoint, like I discussed earlier. It is self-adjoint. So it means that the dynamics is manifestly unitary. Unitary. Okay, so you have there's no problem time. So problem time is resolved. Problem time is resolved. Okay, and okay, so you have no constraint anymore because constraint has been solved classically. So there's no quantum constraint to be solved. Okay, so it means that we resolve the problem of quantum constraints. Okay, so the problem I mentioned at the very beginning in this lecture is now completely resolved. It's now resolved in this reduced phase-space quantization. Okay, but the only price to pay is that this physical Hamiltonian, which governs the dynamics, is a little complicated. It's complicated. It is complicated. So to actually study the dynamics, you have to accept that there is a complicated physical Hamiltonian. Because it's still highly non-polynomial. This physical Hamiltonian is highly non-polynomial because each of the operators C and CV, they are non-polynomial because they contain volume operator. And secondly, you have to take the square root, and then you have to take the absolute value and then take the square root. So then it makes the physical Hamiltonian highly non-polynomial. But what I want to say is that the quantum dynamics is still can be studied. Quantum dynamics still can be studied. There are some very recent work by myself and my collaborators, which study this system, and we find a good way to study quantum dynamics in the reduced phase space, and we can do much more than before. So because the advantage of this framework, so we can understand a lot more than before. Okay, and I'm not going to talk about them because they are just they are really very recent works, but you can have a look at some of my recent paper. Okay, so and 5, 9, 8. So these are some examples of calculations you can do in this framework to study the dynamics. Or so I have a recent talk, my recent online talk, so I think you probably all know that there's an international loop quantum gravity seminar, which is online. So I had a talk a few months ago, 2 months ago, about how to make progress in the reduced phase space quantization. Okay. Okay, I think yeah. So I over the time. So that's all discussion about reduced phase space quantization. Yeah, I think I should stop. So is there any question?
Yeah, I have a question.
Okay.
Okay, so when you do Hamiltonian analysis, you specifically pick up a time slice, right, for the action?
Yes.
Okay, so then if you do that for the matter field, you still have the so-called the clock field.
That's right.
So can I understand that as this clock field is located on a single time slice?
It's located in a single time slice. So here it is a family of time slices. So the clock field is so at the very beginning you are just picking up a arbitrary time slice. You are not specifically one time slice. It was you just do a 3+1 decomposition, and you just do any 3+1 decomposition because your field is well, you didn't really well, how to say? So your lapse function and shift vector is arbitrary, right? Okay, so and then when you introduce the clock field, and you just use the value of the clock field to parameterize those family of time slices.
I see.
Yeah, and so each time slice is parameterized by tau, and the coordinate on each time slice is parameterized by sigma. Yeah, and by the value of those fields.
I see.
So then because you have because you have those clock fields, you have those dust fields, and you are using this dust field to fix specific time slice.
I see.
Yeah.
And the observables on that single time slice is diffeomorphism invariant because